Welcome to this new explainer. Today, we're unlocking one of the absolutely coolest and honestly most magical concepts in object-oriented programming, polymorphism. It literally translates to one interface, many forms. If you've ever found yourself completely drowning in a massive sea of if-else blocks and thought, man, there has to be a cleaner way, well, you're in the right place. We're going to see exactly how a single method can behave in totally different ways depending on the object, and how this transforms your spaghetti code into a flexible masterpiece. Okay, let's just quickly run through our roadmap for today. First, we'll explore the intuitive magic of polymorphism. Then we'll look under the hood at static versus dynamic polymorphism. After that, we'll clear up overriding versus overloading, apply it all to a real-world scenario, and finally look at how this elevates your flexible coding skills. So, let's dive right in to Section 1, the magical, intuitive world of polymorphism. Before we get completely bogged down in the technical weeds, let's just look at the word itself. Polymorphism sounds super academic and intimidating, right? But it's actually just Greek. Poly means many, and morph means form. Many forms. In our code, this simply means different objects can take the exact same method call and execute it in entirely different ways. You give one single command, but each object reacts based on its own unique nature. And this brilliantly illustrates what I mean. Imagine we have a base class called animal, with a method for making a sound. Then we create two child classes, a dog and a cat. In our code, we just call that one sound method. The command is identical, but the result? The dog barks and the cat meows. You just dictate what to do, and the object itself knows exactly how to do it. It's pretty much magic. But wait a second. How does the computer actually know which version of that method to run at that exact moment? That question brings us to Section 2, static versus dynamic polymorphism. Time to look under the hood. So, there are two main ways the system figures this out. First up is static, or compile-time polymorphism. This is where the decision of which method to run is determined before the program even executes. The second is dynamic, or runtime polymorphism. Here, the decision is made on the fly, while the program is actually running, based on the object you just created. In dynamic languages, this approach is what gives the system its incredible fluidity. Speaking of dynamic behavior, Python brings a really unique philosophy to this, captured perfectly by this quote. It is not about which class the object belongs to, but whether it performs the required behavior. You might know this as duck typing. Basically, if it walks like a duck and quacks like a duck, it's a duck. Strict inheritance isn't always the point. It just matters that the object actually has the method you're trying to call. All right, moving right along to Section 3, method overriding versus overloading. These two heavy-lifting concepts get mixed up all the time, so let's contrast them. Method overriding is when a child class redefines a method it inherited from a parent class, just like our dog and cat defining their own sounds. Method overloading, on the flip side, is having the exact same method name, but with different parameter types or counts. One is about changing an inherited behavior. The other is about handling different inputs. Now here's a really specific nuance to keep in mind. If you're coding in Python, classic method overloading doesn't actually exist out of the box. You can't just write the same method multiple times with different parameters. Instead, developers rely heavily on method overriding and runtime dynamic behavior to achieve that exact same flexibility. Okay, let's step out of the theoretical mechanics and into Section 4, polymorphism in real-life system architecture. Now, what's really interesting about this is how it looks in a professional code base. Imagine designing a payment system for a massive app. Users might pay with a credit card or maybe crypto. If you don't use polymorphism, your code is going to be entirely clogged with rigid if-else statements checking the payment type. But with polymorphism, you literally just issue one single pay command. And as you can see, the core system doesn't need to know the specifics of the transaction. You issue the pay command to a credit card object, and it handles the bank API and limit checks on its own. Send that exact same pay command to a crypto object, and it connects to the blockchain to verify the wallet. The main system just says pay and lets the specific object handle its own complex logic. It is so clean. Which leads us perfectly into our final section, the art of flexible coding. So, the crucial point is this. Mastering polymorphism is an absolute game changer for your career. It drastically reduces code duplication, gives you a highly flexible structure, and makes maintenance ridiculously easy. Above all, it perfectly adheres to the open/closed principle. Your system is open to extension, like adding a brand new payment method tomorrow, but closed to modification. You don't have to break your existing code to add new features. So, I want to leave you with this. Go take a look at your own code today. Where is there a massive, clunky block of if-else statements that you could entirely replace with the magic of polymorphism? Once you start modeling your code around smart object behaviors instead of rigid data checks, you'll literally never look back. Thanks for joining me for this explainer, and happy refactory.